Our universe is vast and mysterious. We see through telescopes not only other galaxies, stars, and planets, but also the afterglow of the Big Bang itself. But there are some things in the cosmos that we have never seen, some concepts that exist in a strange realm between physics and speculation. Among these, few are as haunting as the idea of cosmic strings. These are not strings in the ordinary sense, nor are they related to the tiny vibrating loops of string theory. Rather, cosmic strings are hypothesized defects in spacetime itself. Infinitely thin, unimaginably dense filaments that may stretch across the cosmos like scars left over from the birth of the universe. If they exist, a single cosmic string, thinner than a proton, could be heavier than Mount Everest, warping space and time around it. To understand how such things might exist, let's take a brief detour through the physics of lentils. A convex lens can focus sunlight to a single point, and a concave lens can spread it out. Both cases, the glass bends light according to its shape. Space-time, too, can warp light if it is curved in the right way. And what warps space and time? According to Einstein's general theory of relativity, it's mass. This means that anything with mass bends space and time around it, just like those lenses bend light. But how does this relate to cosmic strings? Imagine space-time as a trampoline. If you put a bowling ball in the center, it will make the trampoline sag. If you then roll a marble around the edge, it will follow a curved path dictated by the dips and valleys created by the bowling ball. Similarly, massive objects warp space-time around them. And if a massive object happens to be infinitely thin, like a string, it will warp space-time in a unique way. It will create a kind of cosmic lens. Light passing close to it will bend and distort, creating multiple images of whatever lies behind it. It's like looking at a building on the street. The light from the building reaches your eyes. But because the light takes time to travel, you're actually seeing it as it was a fraction of a second ago. So the image you see is always slightly out of date. This is why astronomers can use distant galaxies and quasars to study the early universe. We're literally seeing them as they were billions of years ago. Cosmic strings would be like looking at a building on the street, except instead of being a fraction of a second out of date, the image would be out of sync by millions or even billions of years. It would show us how space and time themselves were distorted around an infinitely dense filament. And these cosmic strings wouldn't just warp light, they would also shake the universe with gravitational waves. Ripples in the fabric of space-time that were first predicted by Einstein. Gravitational waves are created by accelerating masses, but they can also be produced by topological defects like cosmic strings. As the universe expanded after the Big Bang, it cooled, and particles began to condense into various forms of matter. If there were any regions where the symmetry of the cooling process was broken, those breaks would remain as topological defects in the form of cosmic strings. These strings would be incredibly dense, tightly wound bundles of exotic matter and energy that formed when the universe was just a fraction of a second old. Today, they might be up to 10 trillion light-years long, forming a sort of cosmic web that stretches across the observable universe. They could explain the large-scale structure of the cosmos, the way galaxies and clusters of galaxies seem to be distributed along invisible filaments. It's an attractive idea, but like most things in physics, it's all about the evidence. Unfortunately, cosmic strings are so elusive that they may forever remain in the realm of speculation. If they exist, they would have to be extremely rare. Each galaxy in the observable universe would need its own cosmic string. But there's no consensus on exactly how they would appear. Some scientists believe they would be visible as bright, narrow lines of light against the cosmic microwave background. Others think they would look more like tiny bright spots. Either way, current experiments have failed to spot them. For now, cosmic strings remain a tantalizing possibility. A reminder that the universe still holds many secrets, and that the line between physics and speculation is often blurrier than we think. We may never see one, but the hunt for cosmic strings goes on. Pushing the limits of cosmology, particle physics, and astrophysics all at once. Who knows? Maybe one day we will see these elusive relics of the Big Bang, and they will reveal new laws of nature that we never even dreamed of. Or maybe they will remain forever out of reach, forever blurring the line between the seen and the unseen. At issue is not whether grand, unified theories exist, but whether they have any features which could serve as relics of their early presence. Some do, and indeed some features of grand unified theories are so ubiquitous as to be almost universal, namely the domains between the strings. Now what's interesting about cosmic strings is that, unlike most of the relics of phase, transitions which would have been produced in the early universe, these are eternal. That is to say, they never decay. So once they're formed forever. And it turns out there's a great deal of matter inside them. How much? Well, we don't know. It depends on the details of the theory, but it can be quite a bit. In fact, some models predict that it's more massive than the entire rest of the universe. In other words, the great bulk of matter in the universe is trapped inside these thin filaments. So that means that all of the stuff we normally associate with matter, you and I, the Earth, the Sun, the galaxies, all of that is just a tiny, tiny part of the total. What we call matter is just a few parts per million of the actual constituents of the universe. How does this happen? Well, again, it's because these things are so incredibly dense. For example, suppose these strings are as thin as 10 to the minus 33 centimeters. A kilometer-long string would weigh as much as the Earth. And since it's so narrow, matter gets piled up along it. Now, exactly how that happens depends on the details of the model. And also, we don't really know what lies beyond the Planck scale. We expect there will be some kind of quantum gravity, some quantization of space and time. But until we understand what that is, we can only speculate. One thing that's difficult to understand is why they don't collapse under their own gravity. After all, they're extremely dense and gravity is very weak compared to the other forces. But remember that the total mass of these things is huge. Indeed, the gravitational attraction between all the stuff inside the string keeps it stable. However, these strings are unstable with respect to quantum effects. They emit particles due to something called the Kibble mechanism. It's named after the British physicist who discovered it in 1977. So, the particles are not emitted from any particular part of the string. Rather, they come from all points along its length. The emission rate depends on the tension of the string. The greater the tension, the greater the emission. But remarkably, the rate is independent of the mass of the emitted particle. Hence, the heavier the particle, the faster the string loses mass. And because of the way these particles are emitted, the string does not lose mass evenly. Instead, it loses mass preferentially at its ends. In other words, the heaviest particles gather at the ends of the strings. Now, it's worth pointing out that this is another instance of the general phenomenon we've observed several times in this series. Processes that build up structures in one regime of mass will tear them down in another regime. For example, gravity builds up large structures out of galaxies, but dark energy tears them back apart. Here, a particle emission process builds up heavy particles at the ends of strings, but then a new particle emission process breaks them back down. It's as though the laws of nature are always trying to reach a balance between order and disorder, sometimes pushing things one way, sometimes pushing things the other. In any case, the upshot of this is that cosmic strings eventually fragment into a vast array of objects ranging in mass from microscopic black holes to neutron stars. That raises a question: what's the fate of those objects? Some will explode as supernova, leaving behind neutron stars. Others will collapse into black holes. Some may form strange stars, whose cores are kept stable by exotic forms of matter. But while all this is going on, the strings themselves will continue to fragment, emitting particles, until they disappear completely. So the universe that results from this process is vastly different from the one we live in. In fact, there's a good chance that no stars would ever form at all. In this universe, black holes would dominate. All the planets and white dwarfs would be gone. Neutron stars would be rare, and the universe would be cold and dark. Fortunately, observations tell us this scenario is unlikely to be correct. That means that either cosmic strings did not form in the first place, or they fragmented long before stars formed. Now, interestingly, the same process seems to have occurred in other contexts as well. For example, cosmic superstrings, which are produced by superconductors above a critical temperature, also fragment into smaller loops that shrink over time. Moreover, these loops often stick together. In fact, the simplest type of loop, called a flux tube, forms a closed necklace-like structure that shrinks in size as it emits particles. These necklaces may also tangle with each other. The end result is a tangled ball of matter. Now, depending on the mass of the original string, the resulting tangled ball could be a neutron star, or a black hole. Interestingly, the evaporation of these strings and the collapse of the resulting tangled balls is accelerating. This is because the larger the collapsed object, the more massive it is. And the more massive it is, the higher the temperature, and the higher the temperature, the faster it evaporates. Thus, in the absence of collisions, the typical size of evaporated objects would decrease with time. Now, note that this is a somewhat contrived example, but it seems plausible enough that physicists have taken it seriously. Indeed, one group of physicists claimed in 2015 to have found evidence of this process in data from the European Organization for Nuclear Research. They said the signature of evaporated objects from cosmic strings could be found in the pattern of particle collisions in their detectors. However, their results were inconclusive, and other experts have argued that the effect they detected could have come from other sources. Still, the possibility remains that one day we may see clear evidence of collapsing cosmic strings. Another interesting aspect of cosmic strings is that because they are created in the early universe, they remain in nearly perfect alignment with each other. By measuring their alignment, we could learn about the conditions under which they formed. But as the universe expands, the angles between neighboring strings changes. And if we assume that the distribution of these strings resembles that of galaxies, we expect there to be fewer nearby strings at higher angles. If this is true, it should show up in the cosmic microwave background radiation. There's already some evidence for this in the Wilkinson microwave anisotropy probe data. However, an analysis published in 2023 argued that it could reasonably be explained by fluctuations in the early universe rather than cosmic strings. Now, one way to tell these apart would be to look for a correlation between the alignment of the strings and the polarization of the cosmic microwave background light. This would require measurements by the upcoming Nancy Grace Roman telescope, currently under construction in California. It's also worth mentioning that cosmic strings would affect the propagation of light. Light would not travel in straight lines as it does in our universe. Rather, it would curve and twist along the strings, making images appear distorted and stretched. This is known as gravitational lensing. It would leave an imprint on the cosmic microwave background radiation. The problem is there are other ways to explain this effect, such as by attributing it to fluctuations in the early universe. Again, the hope is that the Nancy Grace Roman telescope will help to distinguish between these possibilities. Still, given the numerous uncertainties and competing explanations, many physicists think it's premature to draw any firm conclusions. Instead, they would like to collect more data before reaching any firm conclusions. Perhaps someday soon we will finally know whether the universe began with a cosmic symphony or a silent film. Until then, the search continues. There's an old saying that goes, "Show me the data, kiddo, then I'll start believing." It's a sentiment that echoes throughout science. Extraordinary claims require extraordinary evidence. And nowhere is this more true than in the realm of hypothetical objects like cosmic strings. Hypothetical threads of exotic matter that have never been directly observed, despite tantalizing hints and predictions that span almost half a century. In cosmology, a cosmic string is an incredibly dense, thin filament of matter. It's like a thread of matter so small that it would be impossible to see with even the best telescopes, yet so dense that it warps the fabric of spacetime around it. These cosmic threads are hypothesized to have formed in the very first moments after the Big Bang, when the universe was a hot, dense soup of elementary particles. As the universe expanded and cooled, these particles began to clump together. And in some regions, they may have formed these incredibly dense, narrow filaments of matter. If cosmic strings exist, they wouldn't be solitary cosmic hairs, but rather part of a vast network, a cosmic string network, if you will. These networks, if they exist, are a mesmerizing feature of our universe. Imagine them as a tangled mass of filaments reaching across the cosmos, a cosmic web of strange matter. This cosmic string network is not a static entity, it evolves over time. In the early universe, the network was incredibly dense, filled with countless strings crisscrossing the universe. But as the universe expanded and cooled, these strings would interact with each other. They can collide, reconnect, a process known as intercommutation, and change in length, forming closed loops or being stretched taut across vast distances. These string loops would vibrate, and those vibrations would manifest as gravitational waves, ripples in the fabric of spacetime. As the loops cool, they'd shrink, eventually disappearing, but not before sending out bursts of gravitational waves across the cosmos. These gravitational waves could be detected by sensitive instruments on Earth or in space, providing a direct glimpse of this elusive cosmic phenomenon. But that's not all. Cosmic strings would also leave an imprint on the cosmic microwave background radiation, the echo of the Big Bang. In regions where strings exist, the background radiation would be slightly distorted, revealing the presence of these strange objects. Perhaps the most compelling evidence for cosmic strings would come from gravitational lensing. You see, because cosmic strings are so dense, they warp the space-time around them, bending the path of light that passes nearby. This means that if we were to observe a star or galaxy behind a cosmic string, the light coming from that object would be split into two distinct images, each slightly offset from the other. It's like looking at a single object and seeing two copies of it side by side. This would be a clear signature of a cosmic string. In the 1980s and 90s, astronomers were excited to find a few possible candidates for cosmic string lensing. These were pairs of galaxies that appeared to be identical, right down to their shape, brightness, and redshift. The most intriguing case was that of two galaxies discovered in 2003 that seemed to be a perfect example of a cosmic string lens. But further investigation revealed a more mundane explanation. These two galaxies were not images of a single source, but rather two separate galaxies that happened to be close together in the sky. The hunt for cosmic strings continues. Telescopes like Hubble and powerful computers are constantly scanning the skies for telltale signs of these mysterious objects. There are even experiments searching for the gravitational waves they emit, and another experiment looking for the distortions they create in the cosmic microwave background. Despite the lack of definitive proof, scientists remain intrigued by cosmic strings. Their discovery would not only revolutionize our understanding of the early universe, but also point to new physics beyond the standard model. It would be one of the most significant discoveries in the history of science. So here's to cosmic strings, may they be found soon. Or to quote the late great Carl Sagan, extraordinary claims require extraordinary evidence, but they also require extraordinary minds to imagine the possibility in the first place. Imagine you're at a crime scene. A lone detective examining a few strands of hair pulled from a victim's clothing. This is all the evidence you have. Now ask yourself, can you really prove who did this just from a few hairs? It's a tough call without DNA testing. But if the victim had been attacked by a Sasquatch, a unicorn, or a flock of geese, your chances of solving the case would suddenly go up dramatically. That's because some clues point to a very specific set of perpetrators. Now let's swap places. You are the evidence. The Sasquatch, unicorn, and geese are hypothetical explanations for the observation you've reported. The detective is modern astrophysics. Your task is to make the strongest possible case for your existence. How do you do it? It's a question many physicists find themselves asking today, particularly those working on two of the biggest unsolved problems in the field: fast radio bursts and dark matter. Each of these puzzles has a laundry list of potential explanations, from mundane to exotic. So for any given observation, the question isn't usually whether there's a perfectly mundane explanation, but rather, how do we rule out the unicorns and geese? And surprisingly, one creature that keeps entering the discussion is a beast from a whole different zoo: the infamous cosmic string. Cosmic strings are hypothetical, one-dimensional defects in the very fabric of spacetime. Imagine slicing a piece of paper with a blade. If you look closely along the edge of the cut, you see a thin line, the physical manifestation of the paper's two-dimensional surface becoming one-dimensional. A cosmic string is something similar. It's a collapsed higher-dimensional object. It happens in 3 dimensions, it creates a line. Higher dimensions, it creates lower-dimensional defects. Wormholes and black holes are examples of such defects. If they exist, cosmic strings would have formed in the first moments of the universe during phase transitions, just like water vapor condensing into dew on a cool morning. But the strings we're talking about here are much larger. Imagine stretching a tightrope between 2 mountaintops. It's about the size of a cosmic string. In fact, cosmic strings would be so large that by the time the universe cooled below the critical temperature, the strings would already have moved apart by trillions of light years. Yet despite their size, they would still have a profound impact. A cosmic string would warp space around it, creating dips and ripples that affected everything from the paths of comets to the formation of galaxy clusters. There's one problem, though. We have no evidence of them. Scientists estimate that the chances of observing a cosmic string within 100 light-years of Earth are less than 1%. That means unless they are extremely rare, we should have seen one by now. The fact that we haven't led many astronomers to abandon the idea of cosmic strings altogether, but those who believe in them argue that a lack of evidence isn't evidence of a lack. Instead, they say the failure to detect cosmic strings only rules out certain types. Modern searches for cosmic strings focus on their gravitational effects, looking for tiny wobbles in the cosmic microwave background and the large-scale structure of the universe. But that leaves other potential signatures unexplored. Here's the problem. If you want to connect cosmic strings to something like dark matter, you need to add extra physics, like new particles or new forces. And you can't use the same techniques you use to look for the string's gravitational effects. That's why the detective analogy works so well. Sure, you could examine the goose droppings, but if you want to catch the bird in the act, you need a different approach. In other words, if you want to make a case for cosmic strings, you need new observations, preferably something goose-specific. And sure enough, in recent years, theorists have proposed a variety of ways that cosmic strings could reveal themselves, at least indirectly. One example is fast radio bursts. First discovered in 2007, fast radio bursts are intense, millisecond-long flashes of radio waves coming from deep space. About half of known FRBs repeat, while the rest appear once and are never seen again. What's more, some of the repeating bursts seem to come from magnetars, highly magnetized neutron stars. Others show no association with any visible objects. In fact, FRBs were once thought to be a single phenomenon explained by a single mechanism. But the realization that they come in two distinct flavors has prompted theorists to seek two separate explanations. One popular hypothesis suggests that magnetars produce FRBs when their powerful jets bore holes into the cloudy cocoons surrounding young neutron stars. The orphan bursts remain a complete mystery, but some researchers have proposed that they could be caused by oscillating loops of cosmic string known as cusps. Cusps form when two strings collide, briefly moving at nearly the speed of light. That acceleration, in turn, releases bursts of electromagnetic radiation, including in the radio spectrum. This might sound far-fetched, but the energy released in such events could in principle match the observed characteristics of orphan FRBs: short duration, extreme intensity, and wide distribution across the sky. Of course, the fact that cosmic string bursts would be rare and distributed randomly across the universe doesn't match with the fact that we detect FRBs almost daily. Proponents of the model counter that this apparent contradiction doesn't necessarily rule out cosmic strings. They argue that the bursts from strings could hide among signals from magnetars and other sources. In other words, cosmic strings might not explain all FRBs, but they could account for some of the most unusual ones. The so-called orphan bursts, that's one problem solved. But cosmic strings could also help solve the even bigger problem, dark matter. We know it exists because of its gravitational effects. It holds galaxies together, shapes the cosmic web, and makes up about 85% of all matter in the universe. Yet we have no idea what it's made of. The leading hypothesis is that dark matter is made of a particle that interacts only through gravity and a hypothetical new force. But there are a lot of other possibilities, including cosmic strings. In fact, cosmic strings were one of the original dark matter candidates back in the 1980s, unlike the hot dark matter of today. Cosmic strings would have formed heavy, slow-moving clumps in the early universe. As they fell toward massive concentrations of normal matter, they would leave behind wakes that condensed into galaxies and clusters. This idea was elegant, but ultimately it fell out of favor, because observations of the cosmic microwave background showed patterns that matched the predictions of hot dark matter much better than those of cosmic strings. Still, some modern theories suggest that cosmic strings could have played a role in seeding the structure of the universe, either on smaller scales or in combination with hot dark matter. Others propose that cosmic strings could interact with dark matter particles through forces beyond the standard model of particle physics. These interactions could leave subtle imprints in gravitational wave signals, or in the small-scale structure of the universe. And cosmic strings aren't the only way to combine dark matter and fundamental physics. The leading dark matter candidate, the WIMP, or weakly interacting massive particle, is a relic of the early universe. Like cosmic strings, WIMPs were produced in the first moments after the Big Bang. But unlike strings, WIMPs are zero-dimensional. They're point-like particles that interact through a new force. That force would cause dark matter to clump in a way that mirrors the distribution of normal matter, explaining why we see galaxies rotating too fast and why light bends around massive objects. But there's one big problem. While we have no evidence for cosmic strings, we have even less evidence for WIMPs. In fact, they've been ruled out by every direct detection experiment searching for them. That hasn't stopped theorists from trying to resurrect the idea, however. One popular approach is to propose WIMPs that interact with dark matter through multiple channels, including gravity. That way, WIMPs could mimic the gravitational pull of a network of cosmic strings. If true, this would be a remarkable coincidence, and it would also provide a new way of probing the nature of dark matter. To understand this idea, consider the current experiments searching for WIMPs. They typically look for signs of the particle and underground detectors shielded from cosmic rays and other sources of background noise. But such measurements are limited by the amount of time you can keep your detector running. If you want to measure the gravitational effects of dark matter, on the other hand, you don't need to isolate a particle. You only need to know how much mass is in a particular region of space. And there's nothing more abundant in the universe than mass. If WIMPs exist, they would collectively bend space around them just like planets and stars do. But that raises another question. How do you tell the difference between a WIMP and a planet? The answer is that you look for periodic wobbles in the path of a star. And that's exactly what scientists are doing with the upcoming Nancy Grace Roman Space Telescope, which will survey a huge chunk of the sky and look for tiny changes in the positions of millions of stars. Of course, we won't know the results of the Roman survey for several years. In the meantime, there are other cosmic beasts to consider. According to legend, one of the greatest detectives of all time once remarked, "Eliminate the impossible, and whatever remains, no matter how improbable, must be true." It's a good motto for theorists working on dark matter and fast radio bursts. After all, we can't detect these phenomena directly, so we must rely on indirect evidence. As a result, the competition for the best explanation is fierce, and the stakes are high. If you want your explanation to stand out, you need to rule out as many other possibilities as possible. And that's why when it comes to dark matter and fast radio bursts, nobody is safe. Not even geese. What if I told you there's a secret written into the fabric of the cosmos itself, an ancient record of the universe's birth that's been hidden from view for 13 billion years? Well, it turns out that this isn't a fantastical idea from a science fiction novel, but a fascinating possibility that scientists are seriously considering. What they're talking about is the idea of cosmic strings, incredibly thin, nearly invisible threads that stretch across the universe, potentially carrying information about the moments right after the Big Bang. But here's the catch. Despite being theoretically significant, they seem so far out of reach that many people think of them as little more than a curiosity. So here's why we believe there might be cosmic strings written into the universe's fabric. What we hope to learn from them, and why, even if they remain elusive, the search for them matters to us all. The story of cosmic strings. Imagine you're standing on a vast plain, looking out over rolling hills and distant mountains. Now, picture this landscape not as a topographical map, but as a slice through the very fabric of space-time. Here's where cosmic strings come in. Picture long, thin lines running across this landscape, representing disturbances in the fabric of space-time. These cosmic strings, as their name suggests, are incredibly thin, much thinner than atomic nuclei. They're also incredibly long, potentially stretching for billions of light years. The existence of these strange objects arises from certain hypothetical scenarios in the earliest moments after the Big Bang. We're talking about fractions of a second after the universe began, when it was unimaginably hot and dense. As the universe rapidly expanded and cooled during this period, known as the Grand Unified Theory era, different forces that we now have unified: gravity, electromagnetism, and the strong and weak nuclear forces. As the universe cooled, it was like water reaching its dew point. The vapor in the air condenses into clouds, just like when the air around you cools, to the point that water vapor condenses into dew on the grass. Similarly, this phase transition caused some kind of defects in the newly formed particles and fields, and these defects manifested as one-dimensional objects, the cosmic strings. But here's the crucial part. These strings aren't merely relics of the past. They carry within their structure information about the very first instance of the universe. It's like they encode a message from the dawn of time. So why haven't we noticed them? You're right to ask this question. Cosmic strings, if they exist, would have been produced in regions of space larger than galaxy clusters. Yet we observe no large-scale distortions in the cosmic microwave background or the distribution of matter on the largest scales. This apparent contradiction highlights a key feature of cosmic strings. Despite their potential vastness, they would have only been produced in a tiny fraction of the total volume of the universe. Think of it like a cosmic sieve. The universe would have had a lumpy structure on the largest scales due to these strings, but the effect would have been highly non-uniform. Space itself would have been warped and twisted in some regions, while in others, it would have been relatively smooth. Over billions of years, this uneven warping has either stretched and thinned out, or compressed and thickened the fabric of space-time. So while cosmic strings would have affected the entire universe, their influence would have varied greatly from place to place. Some regions have expanded more than others, leading to the large-scale structures we see today: voids, galaxy clusters, and filaments. The search for cosmic strings. Gravitational waves. One way scientists are searching for these elusive threads is by hunting for gravitational waves. Gravitational waves are ripples in the fabric of space-time caused by the acceleration of massive objects. Imagine dropping a pebble into a pond. The pebble is like a massive object, and the ripples that spread out from it are like gravitational waves. But instead of ripples in water, these are ripples in space-time. In the case of cosmic strings, the gravitational waves would have been produced during their formation in the early universe. Scientists are analyzing data from various sources to detect these gravitational waves, including ground-based observatories like LIGO and Virgo, as well as space-based missions like NASA's Laser Interferometer Space Antenna.
Lisa.
The idea is that detecting these gravitational waves could provide direct evidence for cosmic strings. While no conclusive evidence has been found so far, the search is ongoing. A new window into the early universe. The reason scientists want to find cosmic strings goes beyond simply satisfying our curiosity about the origins of the universe. It's because these strings, if confirmed real, would open up a unique window into the early universe. The conditions that might have produced cosmic strings existed only in the first trillionth of a second after the Big Bang, a period of time and energy scale that we can't recreate on Earth. To illustrate this point, consider the Large Hadron Collider, the world's most powerful particle accelerator. It accelerates protons to nearly the speed of light and smashes them together, trying to recreate conditions like those just after the Big Bang. But even the LHC can't get anywhere near the energies needed to produce cosmic strings. Finding cosmic strings would be akin to discovering fossils of a creature that lived before life on Earth began. It would be direct evidence of a past we can only imagine. It would offer insights that no particle accelerator, no telescope, or laboratory experiment on Earth could ever provide. Cosmic strings and the unification of forces. Another exciting aspect of cosmic strings is their connection to grand unified theories or GUTs. These are theoretical frameworks that aim to unify three of the fundamental forces of nature: the strong force, the weak force, and electromagnetism. At enough energy scales, these forces become indistinguishable from one another, and cosmic strings could provide evidence for this unification. If confirmed real, they would offer insights that no particle accelerator, no telescope, or laboratory experiment on Earth could ever provide. It would be like finding a fossil of a creature that lived before life on Earth began, direct evidence of a past we can only imagine. But here's the thing. Many physicists believe that symmetries must break down at these high energy scales. That is, the symmetry between the forces must be lost, giving rise to the different forces that we observe today. Cosmic strings could provide clues to the nature of this symmetry breaking, one of the central processes that shape the cosmos. Relevance for technology and human understanding. Sure, cosmic strings won't give us new energy sources, faster rockets, or medical breakthroughs anytime soon. But their pursuit sharpens the tools that eventually do transform technology. For example, the search for gravitational waves has driven improvements in detector sensitivity and data analysis techniques. These advancements benefit other areas of physics, including the study of black holes and neutron stars. Simulations and modeling used in the study of cosmic strings push the boundaries of high-performance computing, benefiting other fields of science and engineering. And perhaps most importantly, the quest to understand cosmic strings connects particle physics, astrophysics, and cosmology in an unprecedented way, fostering collaboration across traditional disciplinary boundaries. This cross-disciplinary thinking often drives innovation in more practical areas of research. Who knows? The next breakthrough in materials science, nanotechnology, or quantum computing might come from an unexpected insight related to cosmic strings. So what if we never find any evidence for cosmic strings? Even then, the journey would not be in vain. The effects that we might associate with cosmic strings could turn out to be something else entirely. The hunt for cosmic strings has led to improvements in telescopes and data analysis, helping us better understand the universe. And the journey itself fosters collaboration between astronomers, particle physicists, and cosmologists. In the end, the quest to understand the fundamental nature of our reality, even if it leads to a dead end, makes us smarter and more ingenious along the way. And here's the thing. Even if we never find direct evidence of cosmic strings, the research surrounding them advances our overall understanding of physics and the universe. It pushes the boundaries of our knowledge and capabilities, leading to indirect benefits that we can't always predict. Who knows? Maybe the quest to understand cosmic strings will indirectly lead to breakthroughs in other areas of science and technology. Most importantly, the quest to unravel the mysteries of cosmic strings embodies the human spirit of exploration and discovery. It's a testament to our relentless curiosity about the universe and our place within it. It reflects our desire to understand the deepest laws that govern reality and our fascination with the story of creation. Whether or not we find cosmic strings, the journey to find them enriches our understanding of the cosmos and inspires us to keep pushing the boundaries of human knowledge. So remember, the universe is full of wonders, and sometimes the greatest discoveries are the ones we didn't even know to look for. Imagine an infinite array of tiny cracks in space, finer than the finest atom, crisscrossing the universe, stretching from one end of existence to the other. Can you picture them? Neither can we, because they're invisible. These hypothetical cracks, however, are among the most extraordinary ideas in all of theoretical physics. Their name, cosmic strings. Let me repeat after you. What exactly are cosmic strings? Imagine, if you will, a one-dimensional defect in the fabric of spacetime, much like a crack running through a pane of glass. Now, stretch your imagination to the point where this line extends throughout the entire universe, infinitely thin and incredibly dense. That, my friends, is a cosmic string. But don't be fooled by their seemingly simple definition. These cracks in space are not just lines. They are topological defects that emerge when quantum fields, the fundamental forces of nature, condense as the universe expands. The idea of cosmic strings may sound like science fiction, but it emerged organically from decades of theoretical work, experimental searches, and the insatiable curiosity of physicists who dared to imagine what the universe might look like at its most extreme. So let's unravel this cosmic mystery together and discover the human story of how we came to chase these invisible cracks in space-time. First, we need to talk about grand unified theories, or GUTS, which are ambitious attempts to unify three of the four fundamental forces of nature: the strong nuclear force, the weak nuclear force, and electromagnetism. These forces were once believed to be separate, but physicists hypothesized that they could have originated from a single force in the early universe. As the universe expanded and cooled, symmetries were broken, and particles gained masses. Physicists theorized that topological defects known as strings could have formed during this phase transition. These strings were one-dimensional defects in the fabric of space-time and could stretch across the entire universe. In the 1980s, researchers explored if these cosmic strings could play a role in the formation of large-scale structures in the universe. Some scientists even proposed that strings could have served as the seeds for galaxy formation, drawing matter together through their gravitational pull.
Nice.
These ideas were quite speculative, but they captured the imagination of scientists who had been pondering the origins of cosmic structure. But then observations of the cosmic microwave background, or CMB, provided evidence supporting the idea that matter in the early universe was distributed quite evenly. challenging the notion that strings played a significant role in structure formation. However, the allure of cosmic strings remained, and instead of abandoning them, scientists sought to refine the theory. By the late 20th century, the exact mechanism by which these strings could have formed was well established. We learned that the process was tied to a phenomenon known as spontaneous symmetry breaking. You may be familiar with this concept from everyday life. Think of a perfectly symmetrical pane of glass resting on a table. The glass can rotate freely without any external influence. However, once the glass reaches a critical angle, it suddenly falls to the table in a less symmetrical position. This sudden shift from a state of high symmetry to a state of lower symmetry is analogous to the way in which the early universe transitioned from a state of high symmetry to a state of lower symmetry, resulting in the formation of strings. This process is known as the Kibble mechanism, named after British physicist Tom Kibble, who first proposed it. In 1976, with the theoretical framework solidified, the quest for cosmic strings shifted to observation. The 1990s saw the launch of several space-based telescopes dedicated to searching for signs of cosmic strings. One such telescope was the Cosmic Background Explorer, or COBE, launched by NASA in 1989. COBE was designed to measure the temperature fluctuations in the cosmic microwave background radiation, which provided insights into the distribution of matter. Although COBE did not find any conclusive evidence of cosmic strings, it set important constraints on their properties. Another notable mission was the Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001. WMAP provided the most precise map of the CMB at the time, and further tightened the constraints on cosmic strings. Despite these early searches, the question of whether cosmic strings existed remained open. However, as the 2000s progressed, researchers began exploring other ways to detect these elusive entities. Enter gravitational lensing. When light passes by a massive object, it bends slightly due to the object's gravitational field. This bending of light can distort and magnify the image of distant galaxies lying behind the massive object. Gravitational lensing has been used to discover many interesting phenomena in the universe, but scientists wondered if there was a different kind of lensing that could help them spot cosmic strings. The idea was that a cosmic string's intense gravity could warp the fabric of spacetime around it, causing light from distant sources to bend in unusual ways. This would create a telltale signature in the shape of a V when observed from Earth. While this method proved to be challenging, it offered a glimpse into the potential of gravitational observations in the hunt for cosmic strings. Meanwhile, another approach involved studying the cosmic microwave background radiation. The movement of cosmic strings through the plasma of the early universe would create ripples in the CMB. Analyzing these ripples could provide clues about the string's existence. Fortunately, despite numerous searches, no anomalies in the CMB that could be attributed to cosmic strings have been confirmed. As the 2010s approached, the hunt for cosmic strings took a turn toward gravitational waves. These ripples in spacetime were predicted by Einstein's theory of general relativity and had been detected for the first time in 2015 by the Laser Interferometer Gravitational Wave Observatory, or LIGO. Gravitational waves can carry information about the most violent events in the universe, such as the collision of black holes or the explosion of supernovas. Scientists speculated that cosmic strings could also emit gravitational waves as they moved and interacted with each other. This meant that detecting gravitational waves could potentially provide evidence of cosmic strings. Experiments like LIGO and Virgo began scanning the skies for telltale signals. And in 2023, the North American Nanohertz Observatory for Gravitational Waves, or NanoGrav, announced the detection of a low-frequency gravitational wave background. While this discovery was not directly linked to cosmic strings, it demonstrated the growing sensitivity of gravitational wave detectors and raised hopes for future findings. Today, the search for cosmic strings continues. Several experiments are pushing the boundaries of gravitational wave detection in an effort to capture a signal that could revolutionize our understanding of the universe. Meanwhile, others are turning to computer simulations to model how strings would evolve over time and what kind of gravitational wave signals they would produce. So why do physicists continue to pursue this elusive quarry? The answer lies in the profound implications that come with finding even a single cosmic string. Detection of these one-dimensional defects would confirm the occurrence of a symmetry-breaking event in the early universe at unimaginable energies. This discovery would open the door to studying physics at scales far beyond our current reach, potentially unifying theories that now seem disparate. It would be akin to finding the first piece of a cosmic jigsaw puzzle, setting in motion a chain of discoveries that could reshape our view of reality. Think about it. The hunt for cosmic strings is not merely a quest to uncover one of the universe's deepest secrets. It is a testament to the boundless curiosity and relentless spirit of scientific inquiry. It embodies the courage to explore the unknown, the patience to observe, and the brilliance to theorize. It is a reminder that the universe never ceases to amaze, and that our quest for knowledge knows no bounds. They say pictures are worth 1,000 words, but this one goes further. It describes not just what we see, but the origin of what we see. Each loop of this cosmic serpent tells a story of the universe's birth. Here, trapped in time is a moment 10 to the 35th power seconds after the Big Bang. Space is riddled with one-dimensional strings, remnants of a turbulent past. These are not your typical strings. They're one-dimensional rips in spacetime, 100 times thinner than a proton, yet stretching light years across. These are cosmic strings. Born of phase transitions in the early universe, they carry an imprint of the conditions under which they formed, each loop a record of a bygone era. If we could see these relics of creation, they would adorn the night sky like a tapestry, woven with glittering filaments. But let's be clear, we do not see this. We have no direct image of cosmic strings. So how do we know they're there? Or are they merely a figment of physicists' imagination? There is no evidence to claim they exist, only theoretical reasons to believe they could. Yet scientists are pursuing this idea because cosmic strings, whether or not real, force us to confront some of the biggest questions in physics and cosmology. The idea of cosmic strings emerged in the late 1970s during the era of grand unification. Physicists were searching for a common origin of the fundamental forces, and this quest took them back to the dawn of time. At that epoch, the universe was incredibly hot and dense. As it expanded and cooled, energy transformed into matter and radiation. But occasionally, symmetries between forces were broken. These phase transitions, similar to water freezing into ice, released tremendous amounts of energy. Some regions of space rapidly cooled, forming tangled networks of strings that stretched across the entire universe. Today, those networks should still be there, faded but detectable. According to theory, cosmic strings should be everywhere, forming a cosmic web as extensive as the universe itself. Their presence should be felt throughout all of space. It could explain features of the cosmic microwave background, the afterglow of the Big Bang. They could warp and magnify distant galaxies. But have we found any evidence? Sadly, not yet. No experiment has provided an unambiguous detection. Most claims have been debunked or proven to be artifacts of data analysis. So why do scientists persist in searching? Because despite the lack of evidence, the absence of cosmic strings teaches us something. Each year, new telescopes, new detectors, and new theories emerge, pushing the boundaries of our understanding. The groundwork for future discoveries has been laid. And if cosmic strings turn out not to be real, if the universe shows no sign of bearing these scars of creation, it would teach us something equally profound. With each passing decade, we hone our ability to probe the cosmos. If we fail to find strains, that would constrain the models we use to describe reality. The risk of non-discovery drives scientific progress. But let's talk about the promise of discovery. What if we did find cosmic strings? How would that transform our understanding of the universe? To answer this question, we must first understand what makes cosmic strings so intriguing. They are not just theoretical curiosities. They are potential witnesses to some of the deepest mysteries of physics. Cosmic strings are remnants of a time when the universe was in its infancy, when fundamental forces were unified, and when matter was in a primordial soup of energy. They are physical traces of a bygone era, and they hold the key to unlocking the secrets of our existence. You see, the birth of the universe was a violent event. Energy was converted into particles, space expanded rapidly, and forces split apart. These dramatic changes left their mark on the fabric of reality and cosmic strings are the scars of that transformation. These one-dimensional defects are not just relics of the past. They are probes of the deepest questions in physics. They connect the birth of the universe to our present-day reality. If we could observe cosmic strings, it would be like looking back in time to witness the birth of the cosmos. It would be an opportunity to study the conditions that prevailed in the first moments of existence. Imagine for a moment the implications of such a discovery. We would be able to measure the tension of cosmic strings and calculate their density. This information would tell us when specific symmetry-breaking events occurred and shed light on the order of phase transitions that shaped the early universe. We would be able to map the string networks and reconstruct aspects of the early universe that are otherwise invisible. We would essentially have a first-hand account of the universe's evolution from a primordial soup to the world we know today. Furthermore, cosmic strings are closely tied to questions in particle physics and fundamental theory. Their discovery would provide several crucial insights. First, they would offer evidence that grand unified theories are not just mathematical speculation, but part of cosmic history. Second, they would provide indirect support for aspects of string theory, which also predicts extended objects as fundamental ingredients of nature. Third, they would push us closer to a theory of everything, a unified description of all forces, including gravity, electromagnetism, and the nuclear forces. You see, cosmic strings are not just about cosmology. They're deeply rooted in our quest to understand the nature of reality. They connect the largest scales of the universe with the smallest scales of particle physics. In summary, the detection of cosmic strings would revolutionize our understanding of the universe. It would allow us to probe the conditions that prevailed in the first moments of existence. It would provide crucial insights into the birth of the cosmos. It would advance our quest for a theory of everything by offering evidence for grand unified theories and aspects of string theory. Now let's shift our focus to the methods used in the search for cosmic strings. Scientists employ a variety of techniques to hunt for these elusive relics of creation. One of the most promising approaches is the observation of gravitational waves. As massive compact objects move around in space, they disturb the very fabric of spacetime, creating ripples known as gravitational waves. However, cosmic strings possess a unique property. They are expected to produce a continuous background of gravitational waves due to the constant motion of their segments. This gravitational wave background would be a unique fingerprint of cosmic strings. Gravitational wave interferometers, such as LIGO and Virgo, are designed to detect these ripples in spacetime. By measuring the subtle changes in distance between massive mirrors, they can identify the presence of gravitational waves. To enhance the sensitivity of gravitational wave detectors, scientists are building observatories in space. The Laser Interferometer Space Antenna, LISA, planned for launch in the 2030s, will consist of 3 spacecraft forming an equilateral triangle in orbit around the Sun. By leveraging the vast distances between the spacecraft, LISA will be able to detect low-frequency gravitational waves, which are ideal for probing cosmic strings. Another approach to detecting cosmic strings involves observing the effects they have on electromagnetic radiation. Cosmic strings can act as gravitational lenses, bending and magnifying light from distant sources. By studying the distorted images of background objects, astronomers can infer the presence of cosmic strings. Moreover, cosmic strings can induce a change in the polarization of light, known as Faraday rotation. This rotation can be measured by analyzing the polarization patterns of light emitted from sources behind cosmic strings. Furthermore, cosmic strings can influence the dynamics of galactic filaments and clusters. By studying the large-scale structure of matter in the universe, astronomers can search for anomalies that might indicate the presence of cosmic strings. Lastly, direct observations of cosmic strings are also possible. If sufficiently massive, cosmic strings could be detected as objects with unusual properties. For instance, they might appear as point-like sources of light or as elongated structures in the sky. Telescopes such as the James Webb Space Telescope can be used to search for such objects. It's important to note that the search for cosmic strings is not limited to any particular experiment. Rather, it encompasses a wide range of observations and data analysis techniques. By combining results from various experiments, scientists can build a more comprehensive picture of the universe and increase the sensitivity of their searches. In conclusion, the search for cosmic strings is a multifaceted endeavor that utilizes gravitational wave detectors, telescopes, and computer simulations. Each approach provides unique insights into the nature of these hypothetical objects and their potential impact on the universe. While a definitive detection of cosmic strings remains elusive, the pursuit of this mystery drives innovation and discovery across multiple areas of physics and astronomy. Cosmic strings, whether real or not, have led us to develop better detectors, telescopes, and theories. They have pushed us to probe the deepest mysteries of the universe and the nature of reality. If we find them, we will rewrite our understanding of creation. If we don't, we will refine the boundaries of the possible. Either way, we are forever changed by the quest.